Good day everyone, I am JUL-ARSER from BSN Sciences 3A, and today we are talking about measuring of stellar masses. So one of a star's most essential features is its mass, or how much matter it contains. We can estimate how a star will shine and what its final fate will be if we know its mass. As we will see, however, directly measuring the mass of a star is extremely difficult. We need to place a star on the cosmic equivalent of a scale in some way. Fortunately, not all the stars live in isolation from other stars like the Sun. Half of the stars are binary stars, which are two stars orbiting each other and are held together by gravity. So, binary star masses can be determined using orbital observations, just as the mass of the Sun can be computed using by the orbits of the planets that orbit it. These are our objectives for today's lesson. First is distinguish the different types of binary star systems. Second, understand how we can apply Newton's version of Kepler's third law to derive the sum of star masses in a binary star system. Third is apply the relationship between stellar mass and stellar luminosity to determine the physical characteristic of a star. So, we'll take a deeper look at the stars that appears in pairs before discussing how mass can be calculated in greater detail. So in 1650, a little than a half century after Galileo began observing the sky with a telescope, the first double star was spotted. The star Mizar in the middle of the Big Dipler's handle appeared through his telescope as two stars, according to the Italian astronomer Gian Battista Riccicelli, 1598 and 1671. Thousands of binary stars have been discovered since then. Any pair of stars that appear to be close to each other in the sky is referred to as double star by astronomers. However, not all these stars are physically related. Some are simply coincidences between the stars that are different distance from us. Although pairs of stars are the most common, there are also triple and quadruple systems. Seven observations of the reciprocal revolution of two stars, one of a brown dwarf and the other is the ultra cool L dwarf, are shown in this diagram. Each red dot on the orbit represented the blue ellipses represents the relative position of one of the dwarfs to the other because some photographs were acquired using the Hubble Space Telescope and others were shot from the ground. The pair of stars appears differently on separate dates. So the arrows led to the actual observation that correlate to each red dot's location. An international team of astronomers used these observations to determine the mass of an ultra-cool brown dwarf star for the first time. The dwarf star is about the size of a Jupiter, has only 8.5% of the mass of our Sun. So, Edward C. Pickering, 1946 to 1919 at Harvard, discovered a second class of binary stars in 1889, a class in which only one of the stars is actually seen directly. He was examining the spectrum of Mizar and found that the dark absorption lines in the brighter star spectrum were usually double. Not only were there two lines where astronomers usually saw only one, but the spacing between the lines was also changing. The lines even became single at times. Pickering accurately deducted that Mizar A, the brighter component of Mizar, is actually two stars rotating around each other every 104 days. Um, a spectroscopic binary is a star that looks as a single star when photographed and examined visually through a telescope, but is revealed to be double star by spectroscopy. Now let's go to the fifth slide. Both stars in a binary star system orbit their mass center. The graphic depicts the relative position of two stars of different masses relative to their center of mass, similar to how two masses on a seesaw must be situated to keep it level. The star with the larger mass will be located closer to the mass center, while the star with the lower mass will be found further away. So depicts two stars A and B moving about their center of mass, as well as one line in each star spectrum that we witness at different times from these systems. When one star approaches us from the center of mass, the other star moves away from us. Because star A is traveling toward us in the top left figure, and the line in the spectrum is roughly shifted toward the blue end of the spectrum. Because star B is traveling away from us, its line is red shifted. The line looks twofold when we look at the combined spectrum of the two stars. When two stars move across our line of sight, um, their radial velocity is the same, so the spectral ratio is the same. So because one star is traveling toward Earth while the other is moving away, we notice changes in velocity. Half a cycle later, the scenario is reversed. The spectral lines shifted back to the fourth due to the Doppler shifts. Lines from both stars may be observed far separated from each other in schematics 1 and 3. The two lines are identically overlaid when the two stars are traveling perpendicular to our line of sight. That is, they are neither moving toward away from us. Therefore, we only see a single spectral line in picture 2 and 4. The orbit of the star pair is tipped slightly to with regard to the observer in the diagrams, or would be tilted with respect to the viewer's line or the sight of viewer we're looking at in the sky. So if the orbit were exactly in the plane of the page of the screen, the sky would appear to move back and forth in a straight line, and we would see the largest possible radial velocity variations. If the orbit were perpendicular to the plane of the page or screen, the stars would appear to move back and forth in a straight line, and we would see the largest possible radial velocity variations. A radial velocity curve is a graph that shows how the velocity of stars change over time. The curve of the binary system is illustrated in the next slide. Now let's go to the next slide. So this chart depicts how two stars in a spectroscopic binary system alternately approach the recede from Earth by plotting their radial velocities. Positive velocity indicates that the star is traveling away from us in relation to the system's center of mass, which in this case is 40 kilometers per second. Negative velocity indicates that the star is traveling away from the center of mass and toward us. The diagram numbers 1 to 4 correspond to the points of the curve that correspond to the image in link. Let's go to the next slide. So, using Newton's reformulation of Kepler's third law, we may estimate the masses of the binary star systems. Kepler's discovered that the time it takes a planet to orbit the sun is related to its distance from the sun by a mathematical formula. If two objects are in mutual rotation in our binary star situation, the period, or the p, which they revolve around each other, is related to the semi-major axis, or the d, of one's orbit with regard to the other, as shown in this equation, where d is in astronomical units, p is in years, and M1 plus M2 is the total of the two stars' masses in units of the sun's mass. This is a highly important formula for astronomers. It states that we may determine the total of the mass of two stars in a binary system if we know the radius of their orbits and the period of mutual revolution. What is the maximum mass of a stars can have? Stars with masses greater than the Sun are uncommon, within 30 light years of the Sun. None of the stars have mass higher than 4 times that of the Sun. A few stars with masses up to around 100 times that of the Sun have discovered by researchers at great distance from the Sun, and a handful of stars, a few out of several billion, may have masses as enormous as 250 solar masses. Most stars, on the other hand, are smaller than the Sun. A real star can have a mass of around 1 to 12 that of the Sun, according to theoretical calculations. Astronomers defined a true star as a one that develops hot enough to fuse photons into helium. As discussed in the Sun, a nuclear powerhouse. Nuclear processes using deuterium can provide energy for a short time in objects with masses between 1 over 100 and 1 over 12 that of the Sun, but they do not become hot enough to fuse photons. The region surrounding the trapezium star cluster inside a star-forming region known as the Orion Nebula is shown in these Hubble Space Telescope photographs. 8. There are no brown dwarfs visible in visible light because they emit very little light in visible light and are concealed within the dust clouds in this region. B. This image was captured using infrared light, which can pass through dust and reach us. Brown dwarfs with masses ranging from 13 to 80 times that Jupiter are the faintest object in this picture. Planets are even smaller objects with masses less than 1 over 100 of the mass of the Sun, or 10 Jupiter masses. They may emit energy generated by the radioactive materials they contain, as well as heat produced by slowly compressing under their own weight, a process called gravitational contraction. Their innards, on the other hand, will never reach temperature high enough for nuclear reaction to occur. Jupiter, for example, with a mass around 1 over 1000, that of the Sun, is obviously a planet. We could only discover planets in our own solar system until the 1990s, but now there are thousands of them all over the universe. Let's go to the next slide. The mass and luminosities of stars are presented by the plotted points. White dwarf stars make up 3 points below the sequence of points. This can also be expressed mathematically. So L times m raised to 3.9. The fourth power of the mass in units of the Sun's mass varies as luminosity, given in units of the Sun's luminosity. If two stars differ in mass by a factor of 2, the more massive one will be 24, or about 16 times brighter. If one star is 1/3 of the mass of another, it will be around 81 times less luminous. To sum everything up, the masses of the stars can be determined by the analysis of the orbit of the binary stars. Two stars that orbit a common center of mass. In visual binaries, the two stars can be seen separately in a telescope, where in a spectroscopic binary, only the spectrum reveals the presence of the two stars. So stellar masses range from about 1 to 12 to more than 100 times of the Sun's mass, in rare cases going to 250 times of the Sun's mass. Objects with masses between 1 to 12 and 1 to 100 of the Sun are called brown dwarfs. Objects in which no nuclear reactions can take place are planets. The most massive stars are, in most cases, also the most luminous, and this correlation is known as the mass-luminosity relation. And that's all for our discussion. Thank you for listening.